welcome back. Last time we told the story of L'Hopital and Bernoulli, calculus's most famous priority dispute. Today we close out the differential calculus series with arguably the most useful single result we've covered, Newton's method. A root-finding algorithm that takes the simple geometric idea of a tangent line and turns it into the engine inside every calculator, every computer algebra system, every solver in scientific computing. The setup is dead simple. You have an equation f of x equals 0 that you cannot solve algebraically. Pick a starting guess. Draw the tangent line. Where the tangent crosses the x-axis is your next guess. Iterate. That's the whole algorithm. What's miraculous is the speed. Each iteration roughly squares the error, so the number of correct digits doubles every step. 3 becomes 6, becomes 12, becomes 24. We'll derive the formula, watch it solve a transcendental equation in 4 steps, rediscover an algorithm the Babylonians had 4,000 years ago, look at the spectacular ways it can blow up, and tell the story of how 3 different mathematicians across 70 years built the form we use today. First, the problem. Most equations cannot be solved with a formula. You learned the quadratic formula in high school. Cubics and quartics do have formulas. Cardano's formula for the cubic, Ferrari's for the quartic, but they're horrible and rarely used in practice. For quintics and higher polynomials, there is provably no general formula in terms of radicals. This is the Abel-Ruffini theorem from 1824, sharpened by Galois in 1832. It is a theorem, not a limitation of our cleverness. And once you leave polynomials, it gets worse. Try to solve cosine of x equals x. That equation has exactly one real solution. You can prove it has a solution, you cannot write it down as a formula. Try x times e to the x equals 1. That's a famous one. The solution is a special constant called the omega constant, but again, no elementary formula. Or tangent of x equals x, which has infinitely many solutions, none expressible in closed form. So how does a calculator find the value when you ask for these? It iterates, and the canonical iteration is Newton's method. The idea. You want to solve f of x equals 0. You don't know the answer, but you have a guess. Call it x naught. Here's the insight. Near that guess, the curve y equals f of x is very well approximated by its tangent line. The tangent line is just a line. Solving a linear equation is trivial. Find where the tangent line crosses the x-axis. That's your next guess. Then repeat, tangent line at the new point, find where it crosses 0, that's your next guess. The strategy is to replace one hard problem, solve the nonlinear equation f of x equals 0 with a sequence of easy problems, solve the linear equation tangent equals 0 over and over. Each linear solve nudges you closer to the actual root. If the geometry cooperates, you converge. And as we'll see, you converge very fast. One more way to see why this works, connecting it to ideas we've already built. Back in episode 10, we introduced local linearization, near a point x sub n. The function f is well approximated by its tangent. F of x is approximately f of x sub n plus f prime of x sub n times the quantity x minus x sub n. That's the linear approximation, the first 2 terms of the Taylor series. Now think about what we're trying to do. We want f of x equals 0. The honest equation f of x equals 0 is hard, but the approximated equation, replace f with its linear approximation and set that to 0, is trivially linear and trivially solvable. Set 0 equal to f of x sub n plus f prime of x sub n times the quantity x minus x sub n, solve for x, and you get exactly Newton's formula. So Newton's method is conceptually one sentence. Replace f with its linear approximation, solve the linear problem, use the answer as the next guess. It's local linearization deployed iteratively. There's also a slick reformulation worth mentioning. Define a new function phi of x equals x minus f of x over f prime of x. Newton's method is then x sub n plus 1 equals phi of x sub n, a pure fixed point iteration. Roots of f are exactly the fixed points of phi. And if you compute phi prime at a simple root r, the quotient rule will give you 0, because the numerator of the derivative term involves f of r, which equals 0. A fixed point iteration whose derivative is 0 at the fixed point is exactly the condition for quadratic convergence. So Newton's speed isn't an accident, it's hard-baked into the way the formula is designed. Picture. Here's the curve y equals f of x, a smooth function crossing the x-axis at some point, the root we're after. Start at x naught, somewhere to the left of the root. Draw the tangent line to the curve at the point x naught, f of x naught. Follow that tangent down to the x-axis. Where it hits is x1, already closer to the root than x naught was. Now draw the tangent at the new point x1, f of x1. Follow it to the x-axis. That's x2, even closer. After 2 or 3 more iterations, you're indistinguishable from the true root at the resolution of any picture I could draw. That's the whole geometric idea. Now let's turn it into a formula. Derivation. The tangent line to y equals f of x at the point x sub n, f of x sub n has slope f prime of x sub n. In point-slope form, the tangent line is y minus f of x sub n equals f prime of x sub n times the quantity x minus x sub n. We want to know where this line crosses the x-axis, so we set y equal to 0. Minus f of x sub n equals f prime of x sub n times the quantity x minus x sub n. Divide both sides by f prime of x sub n, so x minus x sub n equals minus f of x sub n over f prime of x sub n. Add x sub n to both sides, so x equals x sub n minus f of x sub n over f prime of x sub n. That value of x where the tangent crosses 0 is what we call x sub n plus 1, our next iterate. So Newton's method is x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. One formula derived in 3 lines. Memorize that formula. It's the whole episode. First worked example. Solve cosine of x equals x. This is the classic transcendental fixed point equation, and it cannot be solved in closed form. Step 1. Rewrite as a root finding problem. Let g of x equal cosine of x minus x. We want g of x equals 0. Step 2. Compute g prime. The derivative of cosine is minus sine. The derivative of x is 1. So g prime of x equals minus sine of x minus 1. Step 3. Pick a starting guess. We need a sensible starting point. At x equals 0, g of 0 is cosine of 0 minus 0, which is 1, which is positive. At x equals 1, g of 1 is cosine of 1 minus 1, approximately 0.540 minus 1, which is minus 0.46, which is negative. So the root sits somewhere between 0 and 1. Start at x naught equals 1. Apply Newton's method. x1 equals x naught minus g of x naught over g prime of x naught, which is 1 minus cosine of 1 minus 1, over minus sine of 1 minus 1, which is 1 minus minus 0.460 over minus 1.841, which is 1 minus 0.250, which is 0.750. Round number, x1 is about 0.7504. Plug x1 in again. x2 comes out to about 0.7391. x3 is about 0.73908513334. x4 is about 0.73908513332, matched to 10 digits. 4 iterations. From a guess that was off by 0.26, we reached 10 correct decimal places in 4 steps. That converged value, about 0.73908513332, has a name. It's called the Dotty number, named, apparently, for a French math professor's friend who noticed her calculator always converged to that number when she repeatedly pressed cosine. It's the unique real fixed point of cosine, and we just computed it. Why does Newton's method converge so fast? The answer is a theorem. If f is smooth, say twice continuously differentiable, and the root r is simple, meaning f prime at r is not 0, and your starting guess x naught is close enough to r, then the error at the next step is bounded by a constant times the square of the current error. In symbols, the absolute value at x sub n plus 1 minus r is at most capital C times the absolute value of x sub n minus r squared. That's what mathematicians call quadratic convergence. In practical terms, each step roughly squares the error. If your current error is 1 part in 1,000, that's 3 correct digits. The next error is about 1 part in 1,000,000, 6 correct digits. Then 1 part in 1,000,000,000,000. Then 10 to the minus 24, 3, 6, 12, 24. The number of correct digits roughly doubles every step. After 6 iterations from a halfway decent start, you're at machine precision. 16 digits, the limit of double precision floating point. Compare with bisection, the dumb but safe method where you keep having an interval. Bisection has linear convergence. You get 1 new bit of accuracy per step, which is about 1 decimal digit per 3 steps. To match Newton's 6 iteration output, bisection needs about 50 steps. Newton's method is the difference between done and still computing. Second worked example. Compute the square root of 2. We treat this as a root finding problem. Solve x squared minus 2 equals 0. So f of x equals x squared minus 2 and f prime is 2x. Apply Newton. X sub n plus 1 equals x sub n minus the quantity x sub n squared minus 2 over 2x sub n. Combine the fraction. The numerator becomes 2x sub n squared minus x sub n squared plus 2, which is x sub n squared plus 2, over 2x sub n. Split the fraction. X sub n squared over 2x sub n is x sub n over 2. The remaining 2 over 2x sub n is 1 over x sub n. So x sub n plus 1 equals 1/2 times the quantity x sub n plus 2 over x sub n. Beautiful formula. Average your current guess with 2 divided by your current guess. Start at x naught equals 1. x1 equals 1/2 times the quantity 1 plus 2, which is 1.5. x2 equals 1/2 of the quantity 1.5 plus 2 over 1.5, which is 1/2 of 1.5 plus 1.333, which is 1/2 of 2.833, which is 1.4167. x3 comes out to 1.41421568, already 6 correct digits. x4 matches the square root of 2 to about 13 digits. 4 iterations from a starting guess of 1. Now, and this is one of the best historical Easter eggs in calculus, this formula was known to the Babylonians around 1700 BCE. They had clay tablets that compute the square root of 2 to 7 sexagesimal digits using exactly this iteration. They didn't have derivatives. They had geometric reasoning about averaging rectangles toward squares. But the algorithm they wrote down is, line for line, Newton's method applied to x squared minus capital N equals 0. Newton's method on a quadratic is the Babylonian method. The same iteration was rediscovered by Heron of Alexandria in the 1st century CE, who explained it in geometric terms. Newton rediscovered it again, 1600 years later, in much greater generality. The square root iteration is the special case everyone keeps finding because it's the easiest case. Newton's method is fast when it works, but it can fail spectacularly. 5 common failure modes. First, bad initial guess. The theorem says close enough to the root, and the definition of close enough depends on the function. If you start too far away, you might converge to a different root, or you might not converge at all. For functions with multiple roots, the set of starting points that converge to a given root is called its basin of attraction, and for nasty functions, these basins are fractal, the famous Newton's method fractals you've probably seen. Second, f prime at x sub n equals 0. Tangent line is horizontal. A horizontal line never crosses the x-axis, and the formula has a division by 0. The iteration blows up. Third, oscillation. The iterate cycle. There are toy examples, like f of x equals x cubed minus 2x plus 2 starting at x naught equals 0, where Newton's method bounces between 0 and 1 forever. Fourth, divergence. The iterates wander off to infinity. Try f of x equals arctangent of x starting too far from 0 and Newton's method runs away. Fifth and subtler if the root is a multiple root, meaning f of r equals 0 and f prime of r equals 0, the quadratic convergence degrades. You still converge, but only linearly, so Newton's method needs to be treated with respect. It's locally fast, meaning fast when you start close, but it's not globally reliable. In production code, you usually combine it with a slower but bulletproof method like bisection. Concrete failure picture. Take the function f of x equals x over the quantity 1 plus x squared. It has a single root at x equals 0. Near 0, f looks like x, and Newton's method converges beautifully. But if you start outside a critical distance, say x naught equals 1.5, something interesting happens. The tangent at x naught shoots down to the left, crossing the x-axis at x1, which is further from the root on the other side. By symmetry, the next tangent shoots back to the right, but even further. The iterates oscillate and grow without bound. Same function, same algorithm, works near 0, diverges from far away. This is what locally fast, globally unreliable looks like in practice. The basin of attraction for x equals 0 under Newton's method applied to this function is the open interval from -1 to +1. Outside that interval, you diverge. There's no warning sign, the formula just runs away. This is why production code doesn't blindly call Newton from any starting point. A brief history. Newton's method did not spring from Newton's head fully formed. It evolved over 70 years and 3 mathematicians. Start with Newton himself. In 1669, Newton wrote a manuscript called De Analysi per Equationes Infinitas, on analysis by infinite equations. The manuscript circulated privately among his friends but wasn't published until 1711. In it, Newton describes an iterative procedure for solving the cubic x cubed minus 2x minus 5 equals 0. His method worked by substituting x equals 2 plus p, expanding, dropping higher order terms in p, solving for p, then substituting back. It's equivalent to what we now call Newton's method, but Newton wrote it as a sequence of substitutions, not as a derivative formula. He hadn't yet abstracted the recurrence. 21 years later, in 1690, an English mathematician named Joseph Raphson published a book called Analysis Equationum Universalis. Raphson took Newton's substitution idea and rewrote it as a clean, purely algebraic iteration that you could apply mechanically. Same recurrence, but presented as a recipe. Raphson's version was more popular than Newton's manuscript because it was actually published. Hence the name you sometimes see, Newton-Raphson method. Both Newton's and Raphson's versions are algebraic, neither uses the language of derivatives. That step was taken by Thomas Simpson, yes, the same Simpson of Simpson's rule for integration, in 1740. In a book called Essays on Mathematics, Simpson rewrote the iteration in its modern form. Differentiate the function, then apply the recurrence x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. That's the version we teach. Simpson rarely gets a mention. The attribution stuck with Newton because Newton did it first, and with Raphson because he cleaned it up. Simpson made it modern and the world forgot. How is Newton's method used today? Mostly, it's used inside something else. Pure Newton's method is rarely deployed on its own because the failure modes are too easy to trigger. Production root finders are hybrids. The standard pattern is first use a slow but bulletproof bracketing method like bisection or Brent's method to corner the root in a narrow interval. Bracketing methods are guaranteed to converge. They can't diverge, oscillate, or run away, but they're linear, so they're slow. Once the interval is small enough that you're confident Newton's method will behave, you switch to Newton. The bracketing phase guarantees correctness. The Newton phase delivers speed. Examples in the wild. The square root instruction on Intel and AMD CPUs uses a hardware lookup table to generate a rough initial estimate of the square root of x, then performs 1 Newton step in hardware to polish it to full precision. Total time, a few nanoseconds. The Python function cp.optimize.brentq is a hybrid of bracketing and inverse quadratic interpolation with Newton-like polish. fsolve in MATLAB and SciPy is Newton-based. Your scientific calculator computes inverse cosine, natural log, arctangent, all transcendental inverses, by Newton's method under the hood. And there's a whole family of quasi-Newton methods, BFGS, LBFGS, and friends, that extend Newton's idea to high-dimensional optimization, where computing derivatives is expensive and you approximate them. Newton's method is everywhere. You just don't see it because it's wrapped in better packaging. Where we landed. Newton's method solves f of x equals 0 when there's no formula by iterating the tangent line root. The formula is x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n, derived in 3 lines from the point-slope tangent. Convergence is quadratic. The error squares each step, the digits double, provided the starting guess is close enough and the root is simple. We solved cosine of x equals x in 4 iterations and recovered the dotty number. We computed the square root of 2 in 4 iterations and noticed that the recurrence is exactly the 4,000-year-old Babylonian algorithm. Newton on a quadratic is. Heron is the Babylonian method. We cataloged the failure modes, bad initial guesses, zero derivatives, oscillation, divergence, multiple roots, and noted that production code combines Newton with bracketing to get the best of both worlds. And the history, Newton wrote it in 1669 as substitutions, Raphson cleaned it up in 1690, Simpson rewrote it with derivatives in 1740. We use Simpson's form, call it Newton's. This is the end of differential calculus. 15 episodes ago, we asked what it means for a function to have a rate of change, and now we have an entire toolkit: limits, the derivative, all the rules, implicit differentiation, the mean value theorem, optimization, L'Hopital, and now Newton's method as the algorithmic capstone. Next time, we flip the direction. Instead of asking what's the derivative of this function, we ask what function has this as its derivative. That's the antiderivative, and it's the doorway into integral calculus, the second half of the subject. Episode 16, Antiderivatives and the Indefinite Integral. See you there! Newton's method is the punchline of differential calculus. The whole edifice, limits, derivatives, tangent lines, linear approximation, collapses into a single recurrence that solves equations you can't solve any other way. The tangent line isn't just a geometric curiosity, it's a tool that, applied iteratively, doubles your digits. Next time we flip the script. Instead of asking E what's the rate of change of this function, we ask E what function has this rate of change. That question opens the second half of calculus. If this episode helped, subscribe. We've got integrals to build. If you got something out of this, please like the video, drop a comment with what clicked for you, or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.